Thank you very much. It's going to be hard for me to compete with the solar eclipse, but I was a bit underwhelmed. I don't know about all of you, so let's see. Maybe I have a chance. Okay, so the title of the talk is very broad and general, but I have to start with a few disclaimers. So the title suggests I'm going to talk about many topics, but instead of going into details about many results, just a dump of plots, I thought I would focus on a specific example as a way to illustrate many recent advances and common challenges that we have in the field. So in particular, I'm not going to talk about deep learning that has replaced shallow learning, which is a very important topic. I'm not going to talk about the very interesting work from the large neutrino experiments. And lastly, there are many LHC results I'm also not going to talk about, in particular B-tagging. Now, in the backup slides, I've prepared some slides which have links to results also in this conference. So I encourage you, if you're interested in any of these additional topics, to please have a look. There are many interesting results, and I apologize in advance that I don't have time to go into them in detail. So what I'm going to do is focus on hadronic final states at the LHC as a way to illustrate, like I said, unifying advances and challenges that we have in the field. So first, what are hadronic final states at the LHC? This is an illustration, a schematic of what a proton-proton interaction might look like. It's very complicated, has many features to it. This is, of course, not to scale. It spans many orders of magnitude. But I'm going to focus in particular about one part of this final state, which is this part here, what are called jets. So you have some hard scatter interaction, and you have outgoing some column-emitted stream of particles, and these are what we call jets. Jets have a lot of structure, and as a result, are very exciting benchmark to use for machine learning. And in fact, jets themselves are defined by machine learning. So jets are clustered using a clustering algorithm. And so the clusters themselves are defined by an unsupervised learning algorithm. And so there's sort of a tight, intimate connection between jets and machine learning. But the difference between these kind of clusters versus, say, normal clusters that you might have in another image, regular image in standard machine learning, is that these clusters have physical meaning. And by that I mean we can calculate their properties in, say, perturbative QCD. But nonetheless, they're a great testing ground for state-of-the-art machine learning techniques, and the results of their structure are physically meaningful and interpretable. There have been some recent attempts to even make clustering algorithms to go into the details of those topics. So let me introduce a framework to talk about jets and machine learning, and I'm going to talk about the jet image. So a jet, as I told you, is a column-emitted stream of particles that hit, say, our detector. A jet image is a fixed two-dimensional representation that is the splash pattern of the radiation that hits the detector. So you can imagine here is the proton are going into and out of the page. You have two jets that go up and down in this case, and they hit the calorimeter, or the detector up here. They leave some energy. And then we take this plane of energy and we unravel it. So this goes here, and the blue part goes here. So we now have a two-dimensional image in roughly cylindrical coordinates. And it's a grayscale image. So the z-axis here is the energy deposited in a given pixel. And this is a nice way to represent the jet, or basically any splash pattern in our detectors at the LHC or elsewhere. And we can then apply some standard machine learning procedures or adopt them as needed on these images. So the first thing you'll note about this image, this is a boosted W boson decaying into two quarks, is that it looks nothing like a natural image. So unlike a cat or a dog or a solar eclipse that has some nice smooth features, there's no smooth features here, right? There's no edges or eyeballs or things like that. And so it's very difficult on an event-by-event basis to tell from this image what exactly it looks like. And in particular, the occupancy is very low. There's no sharp, smooth features. And this is a common challenge in high-energy physics, and in particular for jets, which I'll highlight after the rest of this talk. Now, why images? There are other structures for organizing information, even in fixed representations. But images are nice for many reasons. One of my favorite reasons is that you can just directly visualize the physics. You can look at these images that I've shown here, and you can start to tell a story. So for instance, the picture I've shown here is the average of many boosted W boson decays. And the difference between the top left and bottom right is that I've switched the color structure, so it's going from a singlet to an octet. Otherwise, it's exactly the same. And if you look back, you can sort of see that the radiation pattern is enhanced here in the middle, as you'd expect for a singlet, or enhanced outside for an octet. And this is just the difference of the two images. So you can see by eye already and tell a story, which is great. There's also geometric information encoded in the physical distance between pixels, which is also, of course, important because there's organizational structure that allows it easier for machine learning algorithms to pick up on what's going on. Now, the first topic, which is related to machine learning and deep learning in particular, is about preprocessing. And preprocessing is a very standard step applied in most machine learning algorithms, and it's no different here. And these images, they have some natural symmetries, and you might feel compelled to remove some of the symmetries. So for instance, this is, once again, a boosted W boson jet, and you can see there's sort of like a little energy blob in the middle and then an annulus. And the annulus is because the W decays into two quarks, and there's no particular direction favored, so you see the annulus for the location of the second subjet. And I can trivially remove this by rotating so that the second subjet always points at 6 o'clock down like this. And here I've preprocessed it so you can see that symmetry is removed. However, the images have physical meaning, and so we have to be careful because these preprocessing steps can actually remove or damage the physics content of an image. And this is a very interesting subject. And I don't have time to go into great detail about it, but I want to just give one quick illustration. So let's say, for instance, I have an image, and the mass scale of that image is relevant. So here, my image is very simple. I have only 2 pixels that are hit. I'd say this one at noon and this one at 6 o'clock. And let's say each of them have an energy of 1. So the mass of this very simple, boring image is something like 1.7 in the units of whatever energy I gave. If I rotate such that the 2 particles are at 3 and 9 o'clock instead, the mass has all of a sudden changed. Are not good ones for doing rotations. This is not a Lorentz transformation. And so this is something which is very important because we often want to do rotations like I've done here, where I've simply rotated in these coordinate system that does not correspond to Lorentz transformation. As a result, the physics content of the mass has been damaged. Now, this may not be a problem per se because your machine learning algorithm might be able to unlearn that, but this is an important point that should be taken into account when we do some preprocessing. Okay, so enough of preprocessing. Now let me move to the exciting stuff, which is first classification. And I'm going to talk about deep neural networks applied for classification, regression, and for generation, sort of the 3 big applications. But first, I'll start with classification. It's the most important because we've seen many, many applications. So it's basically binary regression. And I'm going to talk about it only in the context of images. So there's lots of other applications of deep learning, some of which are in the backup slides, and I'd encourage you to have a look. But here I'm going to talk about, in particular, jet tagging. So you have these jets, and you want to identify, using the full radiation pattern inside the jet, what kind of jet is it? Where did it come from? So you can see there are many references here for various tagging applications, so identifying if it's a W boson or a top quark or a quark-quark gluon jet. And we've seen the application of sort of standard machine learning techniques, so like convolutional neural networks, as well as other modern applications. I'll walk through some of those and also some of the important features. And the main conclusion is that deep neural networks universally outperform or at least match physically motivated features. So you can say, for instance, a given jet, let's say it's like a 30 by 30 image, then you're talking about a 1,000-dimensional space in terms of the number of input parameters to the classifier. So that's way more than, say, having a few physically motivated variables that are based on many years of phenomenologists coming up with useful classifiers. So that's good. So this says that the machine learning algorithms can do no worse than those things. They're learning at least what we already knew. Now, what they're actually learning and how much better they do is still a very active area of R&D. Not everyone agrees, because in particular, not everyone agrees on the metric, which is important. But this is still a young field, and I think there's still a lot to learn. But there is a general push, not only for jets, but in many areas of classification, B-tagging, other things, to go lower and lower in the level of inputs. So instead of preprocessing, to do less physics preprocessing or detector preprocessing, and more towards giving directly tracks or calorimeter energy deposits or even hits the lowest level possible objects. And this is proven to be very powerful. But in my opinion, one of the most important things is to try to figure out then what exactly the deep learning algorithms are learning. They seem to be learning something useful and something powerful, even beyond what we already knew about. So now the onus is on us to try to figure out exactly what they're learning. And there are many techniques for doing that. Images are quite nice because they afford a lot of natural visualization. And I've shown up here 8 different plots which are sort of different ways of visualizing what the algorithm might be learning. And so if you have just jet images, the nice thing is just the images themselves tell you something about what could be learned. So I showed the images earlier, those image differences. This is the same kind of thing. Imagine you have 2 images and you just take their difference from the 2 different classes. It tells you sort of what is the average information available for me to learn. But the other things you can do, so convolutional filters are nice because you can look at the filters. And for, let's say, face recognition, the filters look like eyes and ears and noses. And for jet images, it's a little bit more complicated because these blobs only look like, there aren't eyes and ears and noses and tails to figure out. But there are things like subjets and radiation patterns between subjets. And those are things that could, and maybe if you stare long enough, you might be convinced are learned. There are other ideas as well, like for instance, you could look at which images are the most activating from a network, or look at the correlation between the pixel intensity and the network output, which tells you something about, this is correlation coefficient is a linear thing, but it tells you about the nonlinear spatial dependence of the network output. So we can learn there which areas of the jet are most interesting. And you can tell physics stories about this image, like, oh, for instance, this area here, which is more background-like, is because there's a there's more radiation pattern, more radiation enhanced, or it's more radiation in the middle between the two subjects versus around the two subjects. There are stories to tell. But there are other techniques as well that are useful even if you don't have images. And some of them are very obvious, like looking at the joint distribution between your neural network output and some physically motivated variable. So in this case, it's the numbers, so that how two subjetty a jet is. And you can see that in this case, the deep neural network is learning something very close to that variable. So that's nice. But even if you don't have a variable, what you can do is say, you can reweight or redact, look at small regions of phase space to see if I try to figure out which areas, if I put in known information and then look at what else it's possibly being able to learn. And these are still kind of crude ideas, but I think this is an important, this is a very important task, and it's something that I think is a very active and exciting area of research. Another very important challenge that we have on our hands is modeling. So in high-energy physics, we rely very heavily on simulation. And our simulations are very, very good, which is excellent. But the whole point of deep neural networks in feeding low-level information is that they're able to learn subtle features. And subtle features are hard to model. And so at the end of the day, of course, all that matters is the data. The data are correct, and everything else is our best guess. And here you can see, for instance, this is in the jet image context. These are the average image difference for signal and background for 4 different models. And you can see just by eye that these 4 images don't look the same. So the image difference, so like the most basic thing you can look at, what information is available for discrimination, is different between these 4 models. So this is a very important area. And in fact, one nice solution is to train directly on data. So far, a lot of the work has been to train on simulation, labeled simulation data. But there are some nice ideas that are coming up in the literature to train directly on data, even if the data by construction are unlabeled. So this is a plot that shows, for instance, a ROC curve for a new idea based on weak supervision, where you train basically directly on data, not knowing anything, except for what fraction of the 2 classes you have, signal and background. And you can achieve the same performance, so up and to the left is better, for the weak supervision versus the strong supervision. So this is a very nice and exciting field, and I think applies broadly to many aspects, not just jet physics, but many other areas, where you have 2 well-separated classes, but you don't necessarily know on an event-by-event basis if it's signal or background for training. Okay. So the next topic, I talked about classification. Now I want to talk about regression. And regression is, of course, a sort of a generalization of classification where it's not just binary, and you have a more continuous output that you want to look at. And one very natural place to look at that is for the problem of pileup. So this is what a typical event would look like at the LHC, say 10 years from now, where we are colliding not one particle, not proton-proton collision at a time, but we have, say, on a given bunch crossing, you have, say, 200 proton-proton collision. And this is a sort of like an image denoising problem, where you have an image like this, where this one collision is the one we care about, and all those other purple collisions are noise. Now, pileup is a strange sort of noise, because the charged part of the pileup, so particles can be neutral or charged, and the charged one we can identify almost exactly. And it's the neutral part which we can't disentangle from the part we care about, which we call the hard scatter. So it's a little bit different than the standard denoising problem. However, images, in particular pileup, which is doesn't have any sort of local structure, are very amenable to convolutional neural networks. So it's a sort of a standard natural application. And so the idea is you have your proton-proton collision, and you have an image, which is the sum of many components, one of which is the part you care about. So you have neutral charge, neutral that you care about, charge you don't care about, neutral background, charged background. And some of those you know. So the charged background and the charged part you care about, you know. And the neutral part you get is the sum. So you can imagine a case where you have many channels, so images that have multiple layers, so kind of like a red, green, blue image, except there's no red, green, blue here. You can imagine in this case that you have one channel is the charged particles you know about, one is the charged particles from the background, and one is the sum of the neutrals from the stuff you know and the stuff you don't know. And you want to predict the neutral image from the one you care about. So this has been applied and in this recent work. And the results are very encouraging. So here you can see this is the jet mass, which is a very important observable, reconstructed after applying several techniques. And you can see that in this field, people come up with very clever names, some of which sound a little bit scary. And so PUML is no different. So PUML is the machine learning approach. And you can see that more peaked and closer to 1 is better. And in fact, it does seem to work quite well. And it also seems to work quite well for subtle structure inside jets, which is a very exciting avenue because the soft structure inside jets is something particularly hard to model and get right with large amounts of pileup. Okay. So the last topic that I'm going to discuss is generation. So deep neural networks to generate new images. And so here, one technique which is possible is the idea of an adversarial neural network. And adversarial neural networks work by making the training process a game. And games are fun, and neural networks training a GAN is not fun. But the idea is that you train two neural networks, one which transforms noise to images, and one that classifies images as being fake or real. So the idea is here you have some noise, and you have this generator network which basically learns a function from noise to something, hopefully a useful image. And then you have another neural network which decides if the image it got was from the generator, the GAN, or from the physics-based simulator, in this case, Pythia. And we're by now very good at classifying images. So I've talked before about classifying images, jet images in particular. So this side is sort of like a well-established procedure, but this is the new part. And at the end, you don't care about the discriminator. You don't care about telling real images from fake images. What you care about is being able to generate. So at the end, when you train iteratively until the discriminator can't tell if the image is getting a real or fake. And at the end, you have a very good generator, and you cut off the discriminator. And so in this particular case, it's been applied using a variant of convolutional, or something like a convolutional network, which is a locally connected layer. So it's by the locally aware GAN. And here you can see image differences. So it's like the standard discrimination metric for signal and background. In this case, still the W boson I've been using throughout the whole talk. And you can see that the features you see here and here are very similar. So it's learning similar structure, learning to generate similar structure in these images. And you can even project down to the jet mass, which I told you is a very useful variable. And this is actually an interesting feature that we have in high-energy physics images. So we don't have features like eyes and cats and dogs, but what we do have are one-dimensional manifolds which are useful, like the jet mass. And we can look at the jet mass, and it looks like it's well reproduced, at least qualitatively. Clearly, there's more work to make this, ready for actual simulation in a collider application. But it's getting close, and it's moving in the right direction. And you can take this idea one step further, and you can say, well, instead of having just one layer, imagine I had several layers. And instead of having multiple independent layers, suppose I had a causal structure between layers. And this is not unlike a longitudinally segmented calorimeter, for instance, like the Atlas calorimeter. The liquid argon calorimeter has 3 layers, not unlike this one. And you can use something like the jet image approach, except now you have 1 per layer. And this is another interesting challenge because each of these looks not unlike a jet image, but there's a causal structure between those images. And we have a solution which goes by the name CalOGAN. And here you can see some average images from Géant, which is the state-of-the-art physics-based simulator for a calorimeter shower. And here you can see from the GAN, from the deep neural network. And qualitatively, the eye, things look pretty good. When you start to look at the numbers, it starts to become very promising. Here you can see how much faster the CalOGAN is so this is like the physics-based simulator. And these are all numbers for various configurations of the CalOGAN, which you can see are much, much faster. This is very exciting and one of the main ideas behind this approach. And I'm not going to go into all the details about exactly how much, if it's able to reproduce the physics-based simulator, but fortunately there's a talk later in the week, so you can see Luke's talk today about the details, and also Sophia will talk in a plenary session about details related to simulation. But I do want to highlight here that one of the nice features about really pushing on this technology is that there have been very productive interactions with machine learning practitioners. So for Lucan, for instance, or even Ian Goodfellow, who came up with the GAN idea, we've had some positive interactions, and this has helped push us forward. Okay, so I've talked about many things, and before I end, I did want to highlight the point that Atlas and CMS, for instance, have already started implementing some of these ideas in practice. So these are two plots. This is from the Atlas collaboration. This is from the CMS collaboration. A lot more detail and links are in the talks and later in this week. But just to say a few things. So first, the R&D cycle is very fast. So many of you in the room have probably run Keras and are able to train a neural network. So that cycle can be very fast. But then getting it to work in practice in the big experiments of many thousand people can be a little slow. That's OK. It does take some time, and I'm glad we're having these conferences and these discussions to really push the field forward. But it's also good to note there are multiple ways to get to the same solution. So this plot on the top right is a very nice plot from the CMS collaboration. In this case, it's quark versus gluon tagging. But they've really pushed many different architectures and tried various approaches to the problem with low-level inputs. And it's hard to see, but these lines are basically on top of each other. One is based on an image approach, not unlike the one I talked about earlier. And then the other two approaches in this plot are based on other variations that in some ways are very different. So it's exciting to try out many ways. And because the R&D cycle is very fast, we can try out many approaches. And then hopefully the one that's either simplest or more robust, we can try to go through a slow integration cycle to be implemented. And this is a plot of the correlation between the neural network output and the quark-gluon discriminator. So this is a similar, this is basically something similar to this neural network in the Atlas detector, where this tower constituents here just says that the Atlas experiment has studied different inputs. So the same idea, image, but then you could, of course, take different inputs, calorimeter, tracks, various other things, as inputs to the image itself. And there are variations in stability and robustness. And this is also a very exciting aspect that is something you can't get in sort of a phenomenological study. It has to be done within the context of the experiment. So the big experiments are really increasing now their use of deep neural networks. There are many talks at this conference and previous conferences. So I would say this is not going away, and now we should embrace this topic. I hope I've convinced you that deep neural networks, at least for some of the examples I've shown, can be a powerful tool for classification, regression, and generation. And there are many more examples I wasn't able to show, but I hope you'll look at some of the backup slides and attend the other talks this week. But one thing I really want to stress, if you take nothing else from my talk, is that the key to robustness is really to study what is being learned. We're going to apply these neural networks in places we can't always probe them. So we want to be convinced that they're learning something sensible so we can apply them with confidence in new areas of phase space. And we may even get lucky. This may help us learn something entirely new about the standard model or beyond. So thank you very much.
So you talked about using, oh, okay, I see. So you talked about using regression to study pileup. How do you label the data? Do you label on like multiplicity or?
Yeah, so the thing that you predict in this case is an image. So for the jet case, the output of the regression is an image of the neutral hard scatter. So the neutral part of the image you care about. And you take as input images of the charge, neutral, and pileup, and then the sum of the neutral and pileup from the neutral part that you can't distinguish.
Okay, cool. Thank you.
Hi. So I was interested by, I think, one of your first slides where you said that the jets were defined using a clustering. And I was wondering about the interplay between what you call clustering in your network, QCD called clustering. I think they're quite different. So my question is, so the sort of neural network clustering is unsupervised, and it's sort of optimizing the cost function or something like that. Is there an equivalent in QCD? And the second part of the question is, So could we use the old school clustering in QCD in the context of neural network to sort of help clustering? Sorry for the long
Yes, there are a lot of parts to that question, and they're very interesting. First, let me say that clustering that we're used to, jet clustering, is a normal unsupervised learning algorithm. It's agglomerative hierarchical clustering. Those are the jargon words. And the one feature that they have that standard, say, k-means doesn't have is that they're IRC safe. So they're required to be such that, if I combine if one particle splits into two particles, collinearly they're the same, and if you add a soft particle, it doesn't change the clustering algorithm. But you can adopt standard unsupervised learning techniques to have that feature, and that's what I was sort of alluding to here. So for instance, mixture models are like the most, aside from k-means, like it's the generalization of k-means, and it's the most standard clustering procedure, and you can adopt that to be IRC safe. What you get out at the end is not necessarily something more useful than, say, anti-KT, but I think there's still an active area of research. Now to your second question, whether the clustering itself is useful, absolutely. And in fact, the clustering history induces a sequence, a structure on the hierarchical structure. And this has been studied in the context of classifications. You can imagine applying, say, a recurrent neural network where you want to have an ordered structure, and the clustering history provides such a structure. And this has been studied in several places. It's for video, I think, so you have to just shout. Yes. Yeah. So the comparison between CPU here and CPU here is totally fair. It's the same CPU. But what's stressed here in this number is the batch size. So one feature you can get from a neural network from this structure is that you can generate many images at the same time. So if you think about it, like a given proton-proton collision at the LHC may have, say, 1,000 particles in them, and you want to attach to each of those particles a calorimeter shower. So this is a number that's not totally unreasonable to think about. And for more details, I would encourage you to see Luke's talk later today. I think you'll have details of this type. Bang per buck. Yeah, there'll be a discussion later.